All right, I think we're good to get started. Reminder of where we are. We are working on the first half of Chapter 9. And as a quick reminder, the overall structure, what we're going to be working on, 9.1 was an intro to sequences and series, basic vocabulary, basic ideas of what we're going to be covering. 9.2 focused specifically on arithmetic sequences and series. Today we're doing 9.3, which focuses specifically on geometric, and then 9.4 focuses specifically on quadratic. And that's going to kind of be what's going to be our mini unit here, this little half chapter on 9.1 through 9.4. All right. I think we're probably good to get started. Anybody have any problems or questions before we get into this? All right. So first of all, what makes a geometric sequence geometric? A sequence is geometric if the ratios of consecutive terms are the same. So using the generic A1, A2, A3, A4 to represent our sequence, ratios of consecutive terms means if we take A2 and divide it by A1, is that the same as A3 divided by A2, which is that the same as A4 divided by A3, etc. If all those guys are the same, then we have a common ratio, and that common ratio is going to be R. And the one restriction here is R can't be 0, because that makes for a very uninteresting sequence if your ratio is 0. So the number R is the common ratio. Just said that. All right. The explicit formula for a geometric sequence is, in order to find the nth term, it's going to be A sub n is equal to A sub 1 times R to the n minus 1. So A sub n is the nth term of the sequence. A sub 1 is the first term of the sequence. R is the common ratio that we just defined above. And then the exponent's always going to be n minus 1, where n is the number of the sequence. And then sometimes you see it with the subscript notation, and sometimes you see it with the function notation. So every geometric sequence can be written as whatever your first term is, then you multiply it times the common ratio, multiply it times the common ratio, multiply it times the common ratio, multiply it times the common ratio as far as you need to in order to complete however much of the sequence you need. So starting off with a couple basic examples, they're asking us to do two things with these guys here. Write the first 5 terms of the geometric sequence and write a formula for the nth term of the sequence as a function of n. Again, we saw those same instructions yesterday. That's just a fancy way of saying write the explicit formula. All right, so for number 1, they're telling us that A sub 1 is equal to 3 and R is equal to 2. So that means the first term is 3. If the common ratio is 2, that means you're multiplying by 2 to get each one of the next consecutive terms. So multiply by 2, multiply by 2, multiply by 2, multiply by 2, and I think that's 5. 2, 3, 4, 5. We're good. All right, we had talked about yesterday that there are 2 main categories of formulas. You could have an explicit formula, such as one of these guys right here. Oh, I'm sorry, we didn't finish this. We have to write the explicit formula. Okay, so the explicit formula is A sub n equal to, where's it at? The first term is 3. The common ratio is 2. And the exponent is n minus 1. Okay, now on to the second example here. All right, as we talked about yesterday, formulas can be of 2 different types. They can be explicit, such as this. With an explicit formula, you can find any term you want just by plugging the number of the term into the formula. So if we want the 100th term of this pattern, we plug 100 in for n, and that'll tell us the 100th term. We don't need to know anything else around it in order to find the 100th term. Now, in contrast, this guy here is an implicit or a recursive formula. Implicit and recursive both mean the same thing. Depending on the book you go to, the website you look at, those two terms are used interchangeably. With this type of formula, in order to know the 100th term, we'd have to get the 99th. In order to know the 99th, we'd have to get the 98th. In order to get the 98th, we'd have to get the 97th, et cetera, et cetera. So they have to give us some beginning number, and typically it's the first one. In this case, a sub 1 is equal to 9. So that's the first term in a sequence. Then they have to give us some kind of rule that will take us from one term to the next. So right now, we're looking for a sub 2. So if we want a sub 2, that means that the k plus 1 is 2. That means that the k is 1. This is always one term that came before that, or that's always one term that came after that, depending on how you want to read it. So in order to get the second term, we need to take the first term and multiply it by 1/3. I didn't really plan out my space here very well. So 1/3 times 9 will be 3. And then, in order to get A3, we have to take 1/3 of A2. So 1/3 of that is 1. Then, in order to get A4, we have to take 1/3 of A3. 1/3 of 1 is 1/3. In order to get A5, we have to take 1/3 of A4, 1/9, and I think, oops, it's not equal. I think that's 5, right? 1, 2, 3, 4, 5. So those are our 5 terms. Okay, so that's part 1 of what they asked us to do. We wrote the first 5 terms, and we wrote the first 5 terms based on that implicit or that recursive formula. Now we want to write an explicit formula. So it's a sub n is equal to the first term times the common ratio raised to the n minus 1 power. Now this pattern of a sub 1 times the common ratio to the n minus 1 will always get you a formula. That formula you get may not necessarily be the simplified form of what it could be. There's nothing wrong with this. This is acceptable, but it also could be rewritten. We could rewrite 9 as 3 squared. We could rewrite 3 to the negative 1, or rewrite 1/3 is 3 to the negative 1. So that's 3 squared times 3 to the negative n plus 1. We can combine those like terms, and we get 3 to the negative n plus 3. Now, as a free response question, you would not be required to go from there to there. There's no real reason why you had to. But if it's a multiple choice question, maybe you got that and the correct choice is this guy. Or maybe you're checking your answer in the back of the book and you got that and this is how it answers in the back of the book. So you have to be able to potentially rewrite these formulas to make them look a little bit different than what you might get when you just when you plug those numbers in. Good with those? All right, next group here. Find the nth term of the geometric sequence. So for number 3, they're telling us the first term is 3. The common ratio is 3. Given that information, what's the 8th term? So we got 1, 2, 3, 4, 5, 6, 7, 8. So if the first term is 3, that means the first term is 3. Common ratio being 3, so we multiply by 3, multiply by 3, multiply by 3. We only need to get to there. So is it really worthwhile to write a formula? If I'm taking a quiz or test, probably not. I mean, at this stage of the game, you might be able to mental math a couple more, but it's only a few calculator keystrokes. So if you don't have to have a formula for whatever reason, they didn't ask us for one, then don't bother with it. So we're at 81 times 3 times 3 and 2187, 6561. No need for a formula. All right, if you did decide you wanted to write one, or maybe instead of the 8th term, they asked for the 80th term, the formula would be a sub n is equal to, the first term is 3, the common ratio is 3, exponent n minus 1. Plug in 8, or we'll do that anyway. So 3 times 3 raised to the 8 minus 1, and there's your 6561. Oops. Not the clearest. And then last connection before we move off of this question. If you were to write that formula, multiplying two bases are the same, we could add those exponents. An alternative version of that is just 3 to the n. Would be a cleaner way of writing that formula. Good. All right, number 4. Let me copy this, and I'll slide the paper. So we have a sub 3 is equal to 128. A sub 6 is equal to 16. What's the 10th term? So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The third one is 128. 4, 5, 6. This is 16. And ultimately, we want that term right there. Actually, one thing I forgot to mention in the very beginning that we talked about yesterday, unless you're told otherwise, assume we start with a sub 1. Remember, there are problems that start with a sub 0. So far, there's been nothing on this page that indicates we should be starting with an a sub 0. So we're always assuming first term, second term, third term. Okay. So what are we going to do now? We know that this sequence is geometric. So we're multiplying by something to get from here to here. Then multiplying by the same something to get from there to there. And then multiplying by the same something to get from there to there. So 128 times r times r times r gets us to 16. Where 128 r cubed gets us to 16. So r cubed is 16 over 128. R is going to be the cube root of 16 over 128. Why does it glare happen sometimes, not others? So our common ratio is 0.5 or a half. So to get from 128, cut it in half is 64. Cut it in half is 32. Cut it in half is 16. We only need to get to there. So there's really not a reason to have to write a formula. 8, 4, 2, 1. There's our 10th term. Okay, if we did want to write a formula, we need to know this first term. So that would be 256, 512. So it would be a sub n is equal to 512, 1/2 to the n minus 1 power. This is another one, possibly, well, not possibly, 512 is a power of 2, so you could rewrite that into a different form if you felt like you really wanted to or needed to. Perhaps you had some spare time that you wanted to kill. You could rewrite that into another form. Yes?
What if we just, if you
You just have to make sure that you remember that you were going in this direction and then not like reverse it back the other way. But yes, that would work. Like it would be, then it would be times 2 going this way. You wouldn't want to go then times 2 in this direction. Then it would make the numbers go back up again. Did that make sense? Yeah. Okay. All right. Anything else on this? All right. So that takes care of 3 and 4, correct? Those were the 2 we just did? All right. Another reminder from something we talked about yesterday. If you are talking about just a number pattern, like 3, 9, 27, 81, etc., that's a sequence. As soon as you start adding them up, then it becomes a series. Now, for what we do in this class, we can use sequences and series interchangeable. We don't really need to have to make that distinction between the two, but that is the mathematical difference between those two terms. So that's what we're going to get into for the bottom here, which is we're dealing with the adding up a certain number of terms within a pattern. All right, the sum of a finite arithmetic sequence, and this would be the generic way of describing a geometric sequence, with a common ratio, and again, we're not going to let the ratio be 1. We didn't let it be 0. We're not going to let it be 1. It becomes a very uninteresting pattern, is this formula right here. So S sub n stands for the sum of the first n terms, however many you want to add up. A sub 1 is the first term. R is your common ratio, and then that n is there. It's the same n that's here, however many terms you want to add up. So we want to get the sum of the first 7 terms of this geometric series. So one option we could do, we have 1, 2, 3, 4 terms. We could identify the pattern, write the next 3 terms, and add them up on the calculator. And if that's the path you choose to take, there's nothing wrong with that. That's only 7 things we have to add. If it asked us for the first 70 terms, for example, I would recommend against that strategy. All right, so what we need to do in order to use this formula, write that down. We want the sum of the first 7 terms. A sub 1 is the first term. We already know that. It's 5. 1 and 1 are 1 and 1. We know this exponent up here has to match that, so that's a 7. So the missing piece of information we need in order to use this formula is we need a common ratio. So what I'm going to do is go back to the original definition. R is A2 divided by A1, or A3 divided by A2, or A4 divided by A3, any pair that you want to pick. So what we're going to do is we're going to do 15 over 4 divided by 5. 15 over 4 times 1/5. Our common ratio is 3/4. So that means we're multiplying by 3/4 to get from one term to the next. For the purposes of typing this in our calculator, it's a whole lot more convenient to make it 0.75. As long as it's an exact decimal equivalent, you can go back and forth between the fractions and decimals. If it was like 1/3, you don't want to put in like 0.33, you're not going to end up getting an exact answer. You might get real close, maybe you get lucky, but to be 100% accurate 100% of the time, you want to make sure that's exact. Okay, so we got 5, open parentheses, then we're going to want open parentheses again for the top of the fraction. 1 minus 0.75 raised to the 7th power. And then we're closing parentheses for the top of the fraction, divided by new set of parentheses for the bottom of the fraction. 1 minus 0.75, close for the bottom, close for the whole thing. And if we are looking for an exact, what we're going to want to do is fract that answer. And we get somewhat of an unpleasant fraction. But it's not like we have to calculate that by hand. Good? All right. Before we get into the next problem, I'm going to do a quick visualization. Imagine a pizza or your other favorite circular food, a pie perhaps, maybe a cake. It's your call. Use your imagination. Sam, get into your method acting here. You good? Okay. All right. You are going to eat half that pizza. Then you are going to eat half that remains. Then you are going to eat half that remains. Then you are going to eat half that remains. And you're going to eat half that remains. And then you're going to eat half that remains. And you go on up until you are either full, you vomit, or both. Or, in theory, up to infinity. So what happens here is we have the half that you originally ate, plus half of the half, which is a fourth, plus half of the fourth, which is an eighth, plus half of an eighth, which is 16, 1 over 32nd, 1 over 64, blah, 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 blah. So what happens here is ultimately the limit of this, going back to our last unit, is 1 full pizza. So what happens with certain geometric sequences and series is we have an actual limit for that infinite sum of fractions. In this case, it would be 1. So what happens is geometric sequences can converge or they can diverge. Converge means they head to one particular numeric limit. Diverge would be you eat an infinite amount of pizza, in which case that's usually difficult to do. All right. Everybody all right with that basic idea? So on to our last problem here. If your common ratio, well, we don't really do sequences where it's a negative r, at least not today. So if the absolute value of the r is less than 1, so in this case, our r was a half, multiplying by a half each time. The infinite geometric series has the sum. So what we have is a formula that we can use in order to sum up an infinite geometric series that converges, or in other words, an infinite geometric series where the ratio is less than 1. If it's bigger than 1, then it would be like times 2. So you'd have 1 pizza, then you're eating 2 pizzas, then you're eating 4 pizzas, then you're eating 8 pizzas. And that's just too much pizza. Food comas would induce. All right, so this is our infinite geometric series. We want to sum that up, or we're summing from 1 to infinity. In order to use this formula, we need to know that the first term, what the first term is. So in this case, it's 0.2. 1 minus, what's our common ratio? Well, the second term divided by the first term. 0.02 divided by 2. 2 places, 2 places. So that's 2 over 20, or 1/10. So 0.2 divided by 1 minus 0.1. Subtract that answer. 2/9. All right, any problems or questions on that? All right, those of you at home, any problems or questions, stay on and ask. Otherwise, you guys can leave Google Meet